Hello everyone, my name is Chaurasia, country team captain at Nirmaan Hyperloop. Talking about our journey in Nirmaan Hyperloop, we had been founded in 2018 by one of our alumni, Tejas Sharma, with the aim to participate in SpaceX Hyperloop pod competition and also to foster the development of Hyperloop technology in India. Since we founded in 2018, actually journey was quite hurdleful since we started our research phase, and to do research there were multiple domains to be founded, and the students from the different domains, or can we say different department, had come together and formed the team. The approximately number of students were about 15 members, and with the initialization of domain like propulsion domain, mechanical domain, control domain, and braking systems. After team had been established in 2018, in 2019 it was the year when we were more focusing on doing research on the different domain we had founded, and it was also the year when the Taran Boring Company had announced one of the competition, that is a boring competition, where we were selected as a top 50 team among the top 200 team globally who had participated in the competition. It was the same year when we were more focusing on crystallizing the different needs of the different domain, and doing a research on different sections of a different domain. After successful participation in 2019 internal boring competition, in 2020 it was a year to indulge more in the research part of the different domains of Hyperloop. But since we all know the COVID had hit the world, and we had been forced to work remotely either, or maybe sometimes hybridly. So it was a year when team was completely going on. I mean, the team was completely revamping from 15 to 33 members, and it was the same year where I, along with my some of colleague, had been joined the Nirmaan Hyperloop. And to be honest, it was a very tough year to understand the different concepts, since we were in first year and second. Some of us was also in second year, and we started doing research. We started doing understanding the concept. Since COVID was continuing in 2021, also we were forced to work hybridly or remotely from home only, because we were not allowed to work in college as per the government norms. In that year, we were mostly focused on developing the fundamentals and the concepts are required to build our very first pod. We mostly started with the calculation of the different domain. Once the calculation had been done, we were focusing on developing the CADs and the initial phase of the simulations of the different domain, namely mechanical, propulsion, and control loop for the pod. After that development had been done, started to moving on to the manufacturing phase. But before manufacturing, the fundamentals or the dimensions which are required to be solidified need to be done before actually moving into the manufacturing. So that was in another process. Once it been done, we started actually manufacturing our one of our earliest braking systems and propulsion module. So the early phase of iteration had been done in 2021 for brakes and propulsion domain. After that, since 2020, in 2022, we were targeting to participate in European Hyperloop Week, and so for that, documentation has to be done. So we were also mostly focusing on developing the papers and doing research for participation in 2022 European Hyperloop Week competition. Since COVID was continuing in the world and we were forced to work hybridly, or from the work from home as a work culture, and we were not mostly allowed to go in college. We were mostly doing the development of different domains in the Hyperloop, in Nirmaan Hyperloop remotely from our home only. We were taking in weekly basis updates, and most of the requirement which are required to before actually build the fundamentals, or to before build the prototype of the first prod. We were doing the most of the calculation had been done by remotely in that year, and after doing the calculation, it was the time to build the CAD and do the iteration stuff. So we were doing the iterations, and after once it's been done, so different domains manufacturing had been started. Mostly we were mostly focusing on brakings and propulsion section of that period. After that, it was the same year where we were mostly focusing on 2000, that is European Hyperloop 2022, where preparation had been started in 2021 only, in late 2021, and most of the research and the submission work were also in progress. We were mostly focusing on developing the different domains manufacturing, and since we had did the research work and prior modeling and calculation work back in 2022 and 21, so it was a year where we were mostly indulged in the manufacturing segment of our Nirmaan Hyperloop pod. So different domains manufacturing had been done. I mean, the initial testing had been started in that year, as we had opted to present our pod. I mean, for demos, as we had opted for demonstration of pod in 2023 European Hyperloop Week. So we were mostly focusing on the demonstration of pod also. For that, we had developed different I mean, domains. Let's say manufacturing of brakings had been done. The new advanced had been manufactured, along with that frames of the mechanical domain, and suspension part of the mechanical domain had been manufactured so far. So we were near to interfacing of different subsystems into a unique pod. Once it is been developed, we uh, we were trying to actually transport that pod back in the Scotland for participating in European Hyperloop Week 2023, but due to some unforeseen, I mean, circumstances and maybe logistic issues, we were unable to transport our pod on time. So we decided to present our research work so far we had did for developing this different system for for Hyperloop in Nirmaan Hyperloop. After that presentation, I mean, in presentation also we had presented our control and sense domain, and a mechanical domain, and also the complete pod presentation had been presented in European Hyperloop Week 2023. Once the presentation had been done, team come back to India, and we started focusing on other manufacturing of different domains. Let's say the manufacturing of the most advanced linear induction motor had been accomplished in Nirmaan Hyperloop in 2023, and the different stability systems required for mechanical sections we had been manufactured, and there were also subsystems who had been manufactured along with the support structures in Nirmaan Hyperloop.
Hello everyone, my name is Hardik Jain and today I'm thrilled to walk you through the intricate subsystems that power our Hyperloop project. Each subsystem is a piece of a puzzle, contributing uniquely to the efficiency, safety, and groundbreaking technologies of our Hyperloop pod. Starting with the mechanical domain encompassing aeroshell, chassis, brakes, and suspension, let us dive into the nuances of each. First, aeroshell. Streamlined design. The aeroshell's sleek design not only reduces air drag but also ensures optimal aerodynamic performance, allowing the pod to cut through the air with minimal resistance. Thermal regulation. Beyond aerodynamics, the aeroshell contributes to the thermal regulation, protecting the pod from extreme temperatures during its high-speed journey. Material innovation. Leveraging advanced materials like carbon composites, the aerosol ensures a delicate balance between strength and weight, and even enhancing overall pod efficiency. Aeroshell acts as a stage which can cover the entire pod and provide sleek movement of the pod throughout the pod run. Chassis. Modular chassis is the design which is modularly invent adaptations to evolving technologies. Vibration damping. To enhance passenger comfort, the chassis incorporate advanced vibration damping technologies, minimizing the impact of external forces on the pod's interior. Integrated sensor platform. The chassis serves as a platform for various sensors contributing to the overall safety and awareness of the pod surrounding. Let's go with brakes. Regenerative braking. Our braking system isn't just about stopping, it's about efficiency. The regenerative braking system harnesses and stores kinetic energy during deceleration, contributing to the overall energy efficiency of the hyperloop. Energy emergency redundancy. In addition to standard braking, the system incorporates redundant emergency braking mechanisms, ensuring a fail-safe approach in critical situations. Predictive maintenance. Utilizing smart sensors, the brake system predicts maintenance needs, enables proactive measures to ensure continuous and reliable operation. Now, suspension. Adaptive suspension. A suspension system adapts to various track conditions, optimizing the pod's stability during deceleration, acceleration, and curves. Passenger-centric design. Beyond stability, the suspension system prioritizes passenger comfort, minimizing discomfort from dynamic movements and providing a smooth and enjoyable travel experience. Active feedback loop. Integrated sensors provide real-time data on the pod's motion, allowing the system. Let's talk about the rest of the domains: propulsion, sense and control, and power electronics. Propulsion. Let's give a domain overview of how propulsion works. In the context of a Hyperloop pod, the propulsion domain is responsible for the pod's forward motion, determining how it accelerates and maintains speeds along the track. Basic functionality of how propulsion works is propulsion system employs magnetic levitation technology, virtually eliminating friction and allowing the pod to achieve remarkable speeds with minimal energy loss. It is like floating on a cushion of air, enabling a smooth and efficient journey. Let's say a basic example on how it works. Imagine a high-speed train on traditional tracks. The wheels create friction against the tracks, limiting speed and efficiency. In contrast, our Hyperloop's magnetic levitation is a key to gliding on a frictionless surface, enabling faster and more energy-efficient travel. Now, moving forward to the sense and control domain. So, a basic domain overview would be in the Hyperloop context, sense and control form the nervous system of the pod, constantly gathering information along the environment and making real time decisions to ensure a safe and efficient journey. The basic functionality is that the system employs sensors and smart algorithms alongside microcontrollers to understand the pod's surroundings, adjusting for optimal performance and safety. The overall microcontroller system always stays vigilant and ready to respond to changing conditions. The basic example would be thinking of driving a car with adaptive cruise control. The car senses the speed of nearby vehicles and adjusts its speed accordingly. In a similar way, our Hyperloop sense and control system monitors the environment and adjusts the pod's operation to ensure a smooth and safe ride. Usage. The basic functionality would be that the system integrates with smart sensors, optimizing energy consumption and supporting our commitment to eco-friendly transportation. Battery management system is like a smart system which ensures the right amount of energy goes to the right place at the right time. In conclusion, these systems, each with its specific role and functionality, come together to create a revolutionary transportation experience in the form of our Hyperloop project.
Greetings everyone. I am Sayam Jain, a member of Control and Sensing domain at Nirmaan Hyperloop. And today we'll talk about the control and sense subsystem of a Hyperloop pod. But before that, let's talk a bit about the various layers of a Hyperloop system. The first layer is the pod itself. It consists of various advanced propulsion systems, levitation mechanisms, and safety features, along with a myriad of sensors that provide real-time data. This data is passed on to the second layer, which is the controller. It serves as the central hub for overseeing pod operations. And this controller is then controlled by the GUI or the control system, which provides an interface for human interaction with the Hyperloop system. Now you may wonder, where does control and sense come into play here? Well, it is important for each and every layer of a Hyperloop system, as we will see. The control ensures the precise management of the Hyperloop pod's movements, speed, and overall operation through actuation commands. The sensing operations are performed through the sensors that are integrated well into the Hyperloop system. These collect real-time data and makes us aware of the pod's environment. The main objective of controller and sense is to work collaboratively to create a system for optimal Hyperloop pod performance and to record this real-time data and be able to control the pod. Moving on to the sensors themselves. These sensors record vital pod data such as speed, environmental conditions, and enable seamless communication of this data to the central control system for enabling real-time decision making. But why is it so important to have sensors in the pod, monitoring each and every facet of it? After all, pod is mostly mechanical. It can even function without these sensors. But just because you can doesn't mean you should. Sensors are important for data collection, fault detection, redundancy implementation, and feedback for control system. All in all, the data coming in from these sensors allows us to spot anomalies in the functioning of the pod, which then triggers emergency protocols, ensuring the safety of the pod and its passengers. It can also be used to understand which parts of the pod are in need of maintenance or improvement. Moving on, what are the criteria that you should look at to choose these sensors? These are some of the criteria that you can look upon. Keep in mind that these may change depending upon the implementation. Sensitivity and accuracy is an important measure for choosing a sensor. These enable us to uh, make right decisions, and any error in the sensitivity and accuracy can cause huge consequences later on. Moving on, the resolution of the sensors. A higher resolution enables us to take a more precise measurement of the data coming through the sensor and helps us in real-time decision making. Then there is the range of these sensors. For example, let's consider proximity sensors on the pod. These sensors need to ensure that the distance between the pod and the vacuum tube walls are maintained throughout. In these conditions, range of the sensors need to be considered. Then response time, which is a very crucial metric. The response time should be as low as possible during operation. Considering that a pod travels at speeds upwards of 150 to 200 kilometers, any sort of latency could lead to error-prone operation or even worse, certain failures. Then there's the power consumption. We need to ensure that each and every component of the pod is provided with the optimal amount of power throughout its operation. This ensures efficient operation of the pod. And lastly, the environmental conditions. You need to consider whether the pod will be running in open air environment or in a vacuum tube. In either of these cases, your requirements and conditions will vary. To better comprehend the vast number of sensors that are employed in the pod, they can be divided into a few basic categories. Mind you that these categories will vary from each implementation. The first category is the temperature monitoring. During normal operation, certain components of the pod, such as the propulsion system, the mechanical components, and even the electrical systems, may be susceptible to overheating. To ensure that this overheating can be detected and any emergency actuation commands are activated, thermal conditions of the critical components are monitored. Likewise, pressure monitoring systems are also in place to measure the vacuum pressure, pod pressure, and the cabin pressure throughout operation. Any major changes in these values during operation can lead to serious failures. Then there is the power and energy monitoring system. It monitors the power consumption, voltage, current, and overall energy throughout the Hyperloop pod system. The position sensors ensure that there is a consistent gap that is maintained between the levitation systems and the track throughout the operation of the pod. And it ensures that the pod is aligned well with the vacuum tube walls. This ensures a smooth operation of the Hyperloop pod. Then there's the magnetic field measure. It measures the magnetic field produced by the propulsion and levitation system. Now you may wonder, how do all of these sensors come under a single? Well, the answer is a controller. A controller is a compact and integrated circuit that functions as the brain of a Hyperloop system. It contains a processor, memory, and various input-output peripherals that performs the specific task that we want. Some of the common controllers available in the market is the SMT32 and the Raspberry Pi. We have looked at the sensors and the controllers, but how does the data travel from these sensors to the controllers? Well, you will consider the communication protocol between them. First, let us consider half duplex and full duplex. Half duplex allows communication in only one direction, whereas full duplex allows communication in both directions simultaneously. An example of this is the UART. Speaking of which, UART is a serial communication protocol that transfers information bit by bit. It is a short distance protocol which is suitable for a Hyperloop pod since the distance between sensors and controllers is not very large. Then there's the I2C protocol. This is a multi-master, multi-slave protocol that employs a bus structure and support for multiple devices on the same bus. This is suitable since we also have various number of sensors in a single system. Then there's the SPI protocol. It is based on a master-slave architecture and is a full duplex communication between these master and slave. This is often employed in sensor networks and memory interfacing, which is very suitable for our application of a Hyperloop system. After having talked about the sensors, the controllers, and the communication protocol, a question may arise as to how these controllers are programmed for our own pod. Well, you will need to decide upon the coding environment that you use. There are a multitude of options for coding environment and languages available, but you need to choose one that works best for you. Consider the performance of the encoding environment, whether it can provide quick response times during operation. Look into how well supported is the language by the community. This makes sure that even if you run into errors, community solutions are readily available. And also, understand the capability of your and how well suited it is for applications related to the hardware control. Speaking of hardware, it should be understood how well the software can integrate with your sensor network and other systems. It should be perfectly compatible with the microcontroller in use in the pod to ensure smooth communication between the control system and the Hyperloop board. And consider the scalability of the system for any future iterations. So here are a few things you should keep in mind when deciding upon the coding environment. Firstly, always consider the scalability of your system. This makes it easier for software control in future implementations. You need to follow a modular approach to implement the components of the system. This ensures that failure of any one module does not affect the functioning of other modules. Try to follow the solid principles of object-oriented system design, which has been used by professionals to design robust systems. Next is the e-stop or the emergency stop. The emergency stop command is executed once there is an anomaly detected in the sensor readings. This command, once executed, should be implemented indefinitely. The conditions for executing e-stop should be predetermined, and once these conditions are satisfied, the e-stop command should be executed. This mechanism should always work. Then there's the acceleration command, which includes starting and stopping of the pod even under normal operation. These commands should be as precise as possible to give a feeling of intuitiveness to your pod. The command should trigger immediately once actuated. Then we talk about logging. Logging helps us record the sensor data and the pod status throughout the operation of the pod. These commands should be logged for safety and should be timestamped preferably. This aids in identifying issues and optimizing for pod speed in future. And lastly, the latency. The latency should be as minimal as possible during the operation. Suppose your pod is traveling at its cruising speed of upwards of hundreds of kilometers. During this operation, it detects an anomaly in the sensors, and an e-stop command is sent from the offsite terminal to the pod. This command, if it takes too long to reach the pod, may cause trouble and lead to some catastrophic failures. That's why care should be taken to use tech that reduces this latency. Having discussed all of these, let's take a look at what a control system could look like. This is one of the earlier implementations of the Nirmaan Hyperloop control software. This control system was divided into two parts, the front end and the back end. The front end follows the modular approach to designing the component. It means every component of the system can be run and worked on independently. This made it easier to maintain our code. The backend was implemented in such a manner that the two parts, receiving of the sensor data and the transmission of the actuation commands, are run parallel. What this ensures is that there is no break in receiving the stream of valuable sensor data during operation. We also implemented the e-stop functionality into our system. This e-stop command is indefinitely executed once clicked and when it detects any anomalies. There's also the question of actuation. In this iteration, we included the start and stop buttons, which, as you guessed it, starts the pod for its operation and stops it. Then there's the question of logging. All of the commands, the sensor data, and the pod status was saved into a log file during operation. This allows for review later on, and we can help identify the areas where our pod can improve. Also, note, due to following the modular approach, we were able to keep the latency of our communication between our control system and microcontroller down to a minimum. This latency can be improved upon in further iterations. That is all about control and sense. For any further queries, please feel free to contact us. Thank you.